So, what does our model look like? Well, the model has two names that can be used independently. Originally, when this work was invented for Shaky, which was invented at SRI, the language was called STRIPS, which is the Stanford Research Institute Problem Solver language. More recently, in the kind of 90s and 2000s, a new language was invented, which was very similar to STRIPS, which is called the Planning Domain Definition Language, or PDDL. And that became the sort of de facto standard language that planning people use. And now there are 4 or 5 iterations of PDDL. So now people talk about PDDL 1, PDDL 2, 3, etc. And these are languages for describing planning models. So I'll sort of give you on the slides a little bit of technical detail, but we won't focus too much on what some of these technical details mean. If you're someone that's really interested in understanding exactly what this means in terms of logic and maths, then you can read the textbook that goes into more detail. But states are represented by, states are represented by conjunctions, so and, of positive things. So we only represent what is true in the world. Okay? So we only represent what is true in the world. If something's false, we don't include it in the state. And we don't include it in the state because we use something called the closed world assumption. So closed world assumption sort of measures up with this previous one. It says, if I've not written anything down about something, so if my state does not describe something, then I can just assume that that thing is false. Okay, that's the closed world assumption. And this is part of the thing that allows us to have this compact reasoning and representational approach. And we do that using either logical inference, so first order logic, or something called set semantics. So we think about sets, groups of atoms or states. So let's look at a classical planning state. So for a chunk of this lecture, we're going to use a domain called a logistics domain. And in general, planning problems, planning people, call problems domains. So when I talk about a domain, I'm talking about a kind of group of problems that have the same properties. So in this case, we have an airport logistics domain, and I can write down many, many different airport logistics problems using the airport logistics domain. Just as in the Pokemon navigation example, I could have invented many different navigation problems in the same domain. And I could have done that just by changing the map, so where the paths were. I could have done that by changing also where the initial and the goal states were. But overall, the structure of the problem wouldn't change. It would still be the same domain. So for our airport logistics domain, we can express a current state, a state in the following way. Now remember, we only express things that are true. So we express that P1 is a plane, P2 is a plane, BHX and FCO are airports, P1 is at BHX and P2 is at FCO. So this also means that the following things are true. And basically, anything, if you remember, anything that is not positively expressed, we assume to be false. So note that all the things that I say now are true are false things. So it is true that BHX is not a plane. It is true that P2 is not an airport, for example. So this is what the state looks like. The state is a collection of positively stated or true atoms, where atoms are these predicates and kind of logical things inside them. So hopefully you can see already, this is what's called a compositional representation. We can use the form of the logic to compose things. And if you haven't seen this before, that is just a shortcut for saying and. Okay. So this is a Boolean algebra or a Boolean logic. And we'd write or would be written like that. And you can remember that and looks like that because you could imagine there is a little line across. That's how I remember it. Okay. So then we've got actions. The key idea of an action is it only describes what changes happen when they're applied. They don't see anything about what doesn't change, which kind of seems obvious, but it's useful to say. And they have a particular form, so that actions, if you think about our grid world Pokemon example, there's two ways you could have thought of actions. You could have thought of actions, if I write this, you could have thought of actions as go from, let's call this one 3, 3, and then we would have moved to 2, 3. Okay, so if you imagine the grid cells are written as coordinates, and this is what's called a ground action. It describes an exact state change in the problem. But planners use what's called a schema form. And instead, we would just imagine an action called left. And that might have the effect that it changes the value of x to x minus 1. Okay, so the schema form is just kind of saying, let's move left. Whereas the ground form describes exactly what state changes occur. And so we might only have 4 schema actions, up, down, left, and right. But we might have, I don't know, a great deal, right? Hundreds of ground actions. And this is why the classical planning model is a way of compactly representing these problems. We don't need to write down 3, 2, 3, 3 to 3, 2, 4, 4 to 4, 3, 4, 3 to 3, 3, etc. We don't need to write down all those things. We can just write the schema form or the recipe form. So another way to think about that is the recipe, which allows us to create or represent a set of ground actions. So they look like this. And after a couple of slides, I'll pause and take questions. So they look a bit like this. So an action, this is an action for flying a plane from one location to another location. And you've got a couple of features of these actions. So the first off, you have a name and a signature. So the name is fly, and the signature describes all of the values that can go in there, or the variables we're going to use. We have a precondition. So the precondition tells you what needs to be true before you can apply that action. So the preconditions need to be true before the action can be applied. And this kind of makes sense. So here, if you look at the preconditions of the fly action, well, P needs to be an airport. P needs to be a plane. To and from both need to be airports. And P needs to be at the from airport before fly can be applied. And then the effect is a list of the changes that occur within the state. So here the effect is that P is no longer at the from airport, but it is now at the to airport. And here the way to think about it, and we'll go into a little bit more detail in a minute. Sorry, no. There we go. If you see this, if you see the not sign, that's a not. And that also means I'm going to delete this. And here, there's nothing there. So here we're going to add this. So you can imagine we're deleting the first at from the state and adding the next one. And you can see, so this is the schema form, right? Because we've got variables here, okay? These are variables. And then we can instantiate that by putting in values. Okay, now we've got values. So in this case, this is a ground action for flying plane 1. Okay, it looks like, oh, lots of questions. Okay. P is a plane. P is a plane to answer the chat question. And you can see that because, well, okay, it wasn't clear in the well, yeah, it was clear in the previous one, right? So here we're forcing, this basically forces P to be a plane. Or forces P to represent something that we've said is a plane. But that's just the label we're giving it. We don't have to give it that label of P. Okay. Oops. Okay, any questions?
Yeah, quick question. Do we usually include the logic inside the precondition?
You can have richer preconditions than this, but not in this planning language.
Oh, okay.
We'll see in a minute what there is some additional logic that's applied, but here the preconditions can only be positively or negatively expressed things. They can only be true or false and. If you wanted to have or, you would just write a separate action.
Oh, okay.
So if it's the case that P could be a plane or a boat, you wouldn't write like P, plane or boat. You'd write a fly and a... What do boats do? Swim? Boats don't swim. Sail. Boats sail. You'd have a fly action and a sail action, and the precondition of fly action would contain plane, and the fly action, the sail action would be boat. And then when you expanded the state, you could see, can I apply fly or can I apply sail?
So this one PDDL or the stripes or strips?
It's the same. So this is PDDL 1 or strips.
Okay. Thank you.
When we say this is a language, we are not saying that this is a computer language. It's just a representation of the states using predicates, is it?
Yes, it's a modeling language.
Okay.
So this is a way of building a model which is going to express how actions change states. And this is a really, really important thing. Artificial intelligence, almost all of artificial intelligence, is about building models and then solving those models in some way. And what used to be the core part of artificial intelligence was called representations and algorithms. And this is a representation of a problem. It's a way of describing a problem. And if you can standardize your representations and standardize your models, then every researcher and engineer can use them and apply algorithms. So we don't need this. We could write down our planning problem any way we want. But if we express it in this logical way, then we can apply algorithms that other people have written. And we can also understand the mathematical properties of this because people have done that for us already.
Great, thank you.
Cool. Jeremy, do you have a question?
Is this a PDDL some language that can be executed, or just used to express some problem in the situation?
Yeah, it's the same sort of answer that we just had. This is not, you cannot execute this directly. You can, tell you what, later on I'll share a link. You write this into a text editor. So most people now would write this into a text editor, and then you would get an executable that would read the text editor and give you a plan back. So you would write your domain description, which would look like this, lots of actions. You would write an initial and a goal state, and we'll talk about this in a minute. And then a planner would find a plan that applies actions to get you from your initial state to your goal state.
Okay, I got it. Thank you.
Cool. Any other questions? I know this is quite, for those of you that haven't seen this kind of representation before, it's definitely a very new thing.
So it's just a representation. That's all. It's a logical representation so that others see that, they understand it quietly. But in terms of computer language, it's a totally different thing that how you're going to implement it. It's a whole different thing. I understand like that.
Yep, correct. More recently, in the software community, people would call it a domain-specific language. So it's a custom language for expressing properties of problems. But it's a specific type of language that AI researchers invented because it has particular properties that are useful for algorithms and planning. These are really good discussions. Okay, so where were we? So when we're doing our search, we have to know how to expand a state, how to generate the successors. And to do that, we check to see which actions are applicable. Okay, which actions can I perform in which states? So an action is applicable when we say, the technical term is when the state entails the preconditions or supports the preconditions. But that's simply saying, can I match the preconditions to the current state? So here, at the bottom, we've got the preconditions of the fly action, right? And this is saying, can I fly plane 1? And the answer is, in this state, yes, I can. I can fly P1 in that state. Because this state entails the preconditions, which we see down here. But if we change something, we changed stuff on the other side. If we wanted to fly a plane 1 from a different airport, it is not supported, okay? Because this bit is not the same as this bit. Okay, so you're going to get this just kind of pattern matching from the preconditions to the states. And again for this one. We change states, as I said, by doing adds and deletes. So when we apply an action A in state S, we create a new state S prime. So actually, we saw this in an earlier slide, right? Back in last week, we had S, we applied A, and we generated S prime. So if that representation is new to you, I describe that as S prime and the prime is that little symbol up there. And we often, when we're talking about a state transition system, we would often use S, A, and S prime, where S prime is the next thing. So the formula down here is like a recipe for creating S prime. And the way it does it is it takes away the delete effects and it adds the add effects. Right, and if you remember from up here, we've got the delete effects are the negated ones. Oops. These are the delete effects. And the add effects are the ones that are not negated. So I said earlier we're going to use set semantics, and this is expressed in terms of sets. So union, subtraction, these are set operations.
So here,
sorry, could you please clarify what does A mean here?
A is the action. So if we go back here, this is A. So it's just a way of representing that action in a single letter.
Okay, thank you.
So any in this case, any action could be A and any state could be S. And then we create S prime by applying action A to state S.
so hello Nick. So here I see that effect has at negation at P1 BHX.
Okay.
So now this was also
A quick quiz. So we've got a state at the top. We've got our fly action. So which of these states can we generate in one step by applying our fly action? So you can answer. I'll give you a couple of minutes to think about it, or a minute or so to think about it. And the answers can be any number of A, B, C, A and B, A and C, B and C, A, B and C. So it can be any combination of A's, B's, and C's. So the question is, which states result from applying action A, our fly action, to this state? And I'm specifically looking for only like moving one level down in the tree. Okay, I'm going to give you 30 more seconds to decide on an answer, and then I'd like you to all type your answer in the chat. Okay, so 30 more seconds, and then you can all type. In fact, 20 seconds now. All right, go. Type your answers. Collections of A's, B's, and C's. I realize you've all got the slides for this, so maybe you're all looking at the slides. Okay. Pretty much you all got the answer right, which is excellent. So, the answer is B and C. Well done. And let's see. If you didn't get B, C, everyone got B, C, so we don't need to talk about it. And the key thing here is we're thinking about one state. So if we've got this state, we apply the action, we remove, and then we add. And we can't reach this state because that requires applying the action twice successively. So in the question, I was just looking about one action application, and this requires two applications. And that's something that's kind of interesting here. When we think about planning problems for robots, we often want to think about time. How long does it take? How does the world evolve? And there's no time in these problems that we've seen yet. In fact, I don't think we'll ever talk about time too much in these lectures, but it's something I think about quite a lot in my research. So here, time is implicit in the state changes. We haven't given up any time, we've just talked about the orders. So we can think about, and this is another kind of common language modeling thing that we do in AI. We can think about T, and we apply an action, and now we're in a state T plus 1. So we could say that time has moved on 1. And when the state changes, the preconditions are in state T, and the effects occur in state T plus 1. And so, yeah, we can think about, we've got our state. At time T1, we can either have the plane is at P1 is at FCO, or we could have P2 at Birmingham. And the only way we can get the swap is to see the swap is at time T2. So it's only down here, we either see the planes back where they started, or we see the planes swapped over. So when we write down a planning problem, I also sort of mentioned this earlier when people ask me what kind of, what kind of language is it? How do we use it? Well, we typically use it by writing down a domain, which is on the top half of this slide. The domain has the predicates and the actions. And within that domain, we can express a very wide range of problems. So at the bottom of this slide is a specific problem expressed in the language of the domain. So we have the logistics planning domain at the top. We have one possible logistics planning problem at the bottom. And that logistics planning problem is expressed as an initial state and a goal state. So that's how we fully specify a planning problem, with our initial state and our goal state. So now you should be starting to go, oh, okay, I've seen this in the search world. This is now the same in the planning world, right? We've got our initial state and we've got our goal state. Our action language tells us how to move between them, and we'll talk about algorithms in a minute. So some things to note. The initial state must be fully specified. So everything that is true must be included in that initial state. But the goal state only needs to be partially specified. And so partially specified means you only need to write the things you care about in the goal state. So the initial state has to contain everything, because otherwise there's no way of getting it into the problem. But in the goal state, you only really write the things you care about. And so you only really care about, for example, the positions. In this case, we've introduced a new term of cargo. You only maybe care about where the cargo is or where the planes are. You don't care what airports exist in your goal state, because you're sort of assuming that those airports are invariant. You don't care. Okay, the key idea here is the initial state is fully specified, but only a subset of the goal state is specified, so it's partially specified. Right, so we've seen our problems. The question is, how do we find plans? Well, I've already sort of described that we've got our initial state, our goal state. Oh, chat question. Peter, do you mean in between the initial state and the goal state? Okay, so no, the initial state is, think of this like our search problem. In fact, that's what we're going to talk about now. So we're going to think about this as a search problem. Our initial state is the root of the tree. So our trees will be rooted, at least for this slide, will be rooted at the initial state. And then we're going to build that tree by applying actions until we find our goal state. Until we find a state that we find our goal state. And then we can go back through the tree and find the actions. Okay, so there can be many actions in our plan between our initial state and our goal state. And we build the tree. We can build the tree by what's called forward state space search. This is the kind of simplest way about thinking about this. We start with our initial state, and our actions are different our successes are generated by applying different actions to the state. So here we've got our state, we apply P1, we get this state. Here we've got our state, we apply fly P2, and we end up at this state. Okay? So you can imagine this over time building our tree, right? So we would go here and here, and then we're going to build this, just like we saw before. The problem is, for most planning problems, there are just too many states. Okay, because there are typically lots of actions you can apply, lots of different ways of applying those actions. And so uninformed forward search, I forgot to say this actually earlier, so breadth first and depth first algorithms are called uninformed. And they're uninformed because they have no information about the problem. A star and greedy are informed algorithms because they're using a heuristic which contains information about the problem. So here we've got breadth and depth are uninformed algorithms. And here, uninformed forward search must look at just too many states. It's just a terrible idea. So one way to solve this is, instead of going forwards, you can go backwards. So this is a new idea for us today, and it's the idea that we can also search, and this should sort of make sense. We can search backwards from our goal to try and find our initial state, rather than searching from our initial state to try and find our goal state. Now, in the navigation example, in the Pokemon example, it would make no difference. But the key place it makes a difference in the planning problem is because our initial state and our goal state are described differently. So if you remember, our initial state describes everything. And that means there are many possible options for successor states. But our goal state only contains those things that we've said we care about being true. And so that means if we work backwards from our goal state, if we regress from our goal state, then we will only look at states that are guaranteed to be on the path from the initial state to the goal state. So here we can go backwards through our search space. And this is often called in the planning community relevant state search, because it only, in theory, looks at the states that are relevant to your goals, because they are on the path to create your goals. And the idea here is because the goal states are smaller and more compactly specified than the initial state, you will ultimately end up looking at fewer states and actions. It will be faster. So quite quickly, we can write a formula for doing this goal regression in the same way that we could write the forward progression. So when we were doing forward state space, when we were doing forward search, we were using that formula that said S prime equals add and delete. Now, we can also think about regressing back from goal G to a kind of what we call G prime, which is the goal before G. And we do this with kind of and this is, we won't look at this for too long, but it's an interesting thing for you to take away and kind of puzzle over. So when we go backwards from a goal to a sort of sub-goal or a previous sub-goal, now we subtract the add effects of the action that would have got us here, and we add the preconditions of that action to G prime. So this is saying, well, the state that I was in before I got to this goal, if I applied action A, then the preconditions of action A must have been true. So therefore, I add the preconditions of my action to the previous state. And the add effects of the action were only added by the action, therefore I remove them from from the previous goal state. So it's a bit of a confusing one. We won't spend too much time, but I think if you're really interested in exploring this, I'd go and read the textbook or look at these slides a bit slowly. So this is exactly why it works better. So because our goal states are partially specified, each one of our search nodes is representing a collection of states. So previously in our forward search example or our navigation example, each search node represented exactly one state. Now, our goal, if we're doing goal regression, each search node represents a set or a collection of states, and therefore our trees, we're just more efficient because we can look at more states in one go. So here, quick example, the goal state is that we've got this cargo item C1, and we want the cargo item C1 to be at airport FCO. And if that wasn't already true, the way we achieve that is by performing an action which is to unload a package. So we unload cargo C from plane P at airport A. And here, our goal state says we want C1 to exist at FCO, right? So our goal state, let me just draw this on. Our goal state says we want this to be true. Yeah, this is our goal. Assuming that this wasn't already true, we then know we need to unload some cargo from some plane at some airport. Well, in the goal state, we know, well, we want to unload C1 at this airport, right? Because that's here. But there is no plane specified. So then the question is, which plane do we use here? And the answer is, it doesn't matter. So instead, what we do is we place a variable here. So we can use a variable that stands in for the plane variable. It says, you know what, at this point, we don't care which plane we use. And that allows us, again, to express a set of states. Because we're representing this action with all possible planes. Okay. I think we've still got some time. Oh, so this is how this would work. This is something that I think if you're really into planning, is worth going and looking at. There's lots of papers and textbooks on this. It's interesting. If we go back and look at this slide, we said doing forward state space search is bad. So we did two things. We looked at, instead of forward, we looked at backward. But what else could we do to make our search algorithms more efficient on these problems? What else could we do? We didn't want to do backward search. How could we solve these problems more effectively? And the clue is this. Yeah, it's not to do with the initial state. So the problem with, if we don't want to use breadth first and depth first search because they are uninformed, how do we add information to the problem? What's the way that we know about adding information to a search problem? Yes, Torres, Galen, yes, heuristic. Good. We could use heuristics because an uninformed search algorithm doesn't use heuristics, but we could use heuristics to do better. So, the kind of final part of this lecture is about heuristics for planning. And we won't look at this in too much detail, but we want to do informed state space search. And informed search needs a heuristic. If we have a heuristic and it's admissible, i.e. it never overestimates the cost, then A star will find us optimal solutions, which is what we want, and it will find them quickly usually. So this is going to be, in some sense, what we do for many of our planning problems and algorithms. We'll start off by looking at the model, and then we'll think about what do we do to make it faster. And typically when we think about making it faster, we're going to look at heuristics. So what we want is a heuristic. But what is interesting here, and this is something that's quite subtle that we haven't really talked about. Our planning, our PDDL or strips language is a way of describing problems in a domain general way. So it doesn't matter that we've written a logistics domain. We could also have written a block stacking domain or a communication domain or a navigation domain. But if we had written it in PDDL or strips, then any planning algorithm that uses these models, this modeling language, can solve the problems. So that's the key idea. When we've got a planning language like PDDL, we can use any planning algorithm. It doesn't matter that it's logistics or blocks or whatever, because it's the language that is key, not the domain or the problem. But if I was to write a heuristic specifically for the logistics problem, then I couldn't use any planner. I'd have to use one that used my heuristic. So this is a kind of an interesting problem, and one that we'll think about occasionally throughout the course, which is if we want our algorithms to be domain independent, and I'm telling you we do want that, we usually want that as AI researchers, then we need our heuristic to also be domain independent. Okay, so we want to create heuristics, and that usually means, we want to automatically create them. We want to automatically create heuristics, and we would do that from the problem information we've got, right? So the problem information is the domain, the initial state, and the goal state. So we want to look at ways of taking that information and creating an automatic description or an automatic heuristic. But I think, what do I think? Well, okay, we've got like 2 minutes where I will say this, and then I'll start again with this. Just like last time, we'll start again here for the next lecture. But I'll give you something to start thinking about, which is the way we do this is we create something, and this is a really interesting idea in AI. We create something called a relaxed problem. So if you remember at the start of this lecture, I spent some time saying a heuristic should be cheap to compute, cheap to determine. And what's really important is it needs to be cheaper or easier to solve than the main problem. So if you think about the Manhattan distance solution heuristic, that was much easier to compute than the path planning problem was to compute. So when we want to solve a heuristic, we want the heuristic calculation to be easier than the other calculation we're doing. And this is what is known as a relaxed problem. So a relaxed problem is a problem that is easier than the original problem. And the process of relaxation is typically a manual one or an automatic one that makes the problem easier. So we made the navigation problem easier by ignoring the map and just looking at the difference in coordinates. That was a relaxed problem. And we can automatically make planning problems easier. That's one of the key insights of the planning problem of the planning literature, is that we can automatically create heuristics through relaxation. And what we're going to do, the way this is going to work, and I think this will be the final slide of the day, is once we've solved a relaxed problem, so we've got a planning problem, and we need to compute a heuristic for a state in that planning problem. What we're going to do is we're going to take the planning problem and the state that we're interested in, we're going to make it into a relaxed version, then we're going to solve that, and that's going to give us a plan. The cost of that plan, or the solution to that planning problem, we are going to use as the heuristic in the original planning problem. So this might seem a little bit counterintuitive. We're solving one planning problem, our original planning problem. Then for every state that we see, we are going to solve another planning problem, but that's going to be a relaxed version of the planning problem. And the solution to that relaxed version is going to be our heuristic value. And that will work because the relaxed problem is relaxed, which means it's easier to solve. And just sort of to be clear, the Manhattan distance is a relaxed version of the path planning. And the relaxation process is just to ignore obstacles and costs and things. So this is an automatic relaxation that we can perform. And it solves the planning problem because once you've relaxed away the obstacles, you just go straight to the goal.